Hello and welcome to the video for numbers. Today I'll be teaching you types of numbers. Alright, so open to your textbook as already told to you. Now we'll be defining some of the things about numbers. We'll be defining some of the things about numbers, the kinds of numbers that we have. The first one is the natural number. Now, natural numbers are the counting numbers. They are simply the counting numbers, and they begin from 1, 2, 3, 4, 5, 6 continuously to infinity. Okay, the counting numbers are natural numbers. Okay, now we move to the next one, integers. Integers are all numbers, all whole numbers. Whole in the sense that they don't involve decimals or fractions. They are simply whole numbers. Now, integers can be either negative or positive. They also must include zeros. So from negative infinity to positive infinity, all whole numbers therein are called integers. All whole numbers therein are called integers. Then we move to rational numbers. Rational numbers are numbers that are fractions and as well integers. All integers and all fractions are classified together as rational numbers. All integers and all fractions are classified together as what? Rational numbers. Now the last one are the real numbers. The real numbers are all kinds of numbers. Real numbers include natural numbers, integers, rational numbers, and any other number that cannot be expressed as rational numbers, and any other number that cannot be expressed as rational numbers. Like you can see right here on the screen, they include all rational numbers plus numbers that cannot be expressed as fractions, so to speak. Numbers that cannot be expressed as fractions. Now, what are the numbers that cannot be expressed as fractions? They are called irrational numbers. Numbers that cannot be expressed as fractions are called irrational numbers. Okay? And here we have a symbol for all the numbers. You can see that's the symbol for natural numbers, the symbol for integers. The symbol for natural numbers is a designed N. Symbol for integers is a designed Z. Rational numbers, we have the designed Q, and real numbers, we have the designed R. So anytime you see this in your textbook or in the test or in the exam, you should know what each stands for. Now we come to classification of numbers and how they are. Now first we talk about factors. A factor of any number divides exactly into that number. When a number divides exactly to another number, it means there will be no remainder. Okay, so if you pick a number 14, the factors of 14 are numbers that divide into 14 without any remainder. And so we have 1, 2, 7 and 14. 1, 2, 7 and 14. Okay, now let's talk about prime numbers. Prime numbers are numbers that are divisible by 1 and itself only. 1 and itself only. Yeah, I wrote that they have exactly 2 factors. So if you look at all the numbers that have exactly 2 factors, you have 2, 3, 5, 7, 11, 13, 17 and so on. The next number after 17, of course, is going to be 23, because numbers that are only divisible by 1 and itself are 2, 3, 5, 7, 11, 13, 17 and so on and so forth. Okay, that brings us to talk about prime factors. If you look at the statement prime factors talk about prime numbers that are factors of another number. Okay, and as you can see on the screen, a factor of a number which is also a prime number is called a prime factor. Okay, now let's go ahead now and pick examples of prime factors. Write 24 as a product of prime factors. This means that you want to express 24 as a multiplication of prime numbers only. What would you do to get this? You keep dividing by prime numbers until you get to an answer of 1. You keep dividing by prime numbers until you get to an answer of 1. And let's take this step. 24 divided by 2 will give you 12. That's, you are using 2 because 24 is an even number. So of course 2 is the only even prime number you have. So that's why you are going to use 2 first. Of course 12 is still an even number. So you use another 2. And so you get 6. Okay? 6 is still an even number. So you can still use 2. You'll get 3. Now 3 is an odd number and 3 is a prime number. So if you divide 3 by itself, you get to 1. That shows what you have on your far right as the method to use here. So the numbers you have used are 2, 2, 2 and 3. If you multiply these numbers, you will get the answer to the question, because 24 equals to 2 times 2 times 2 times 3. Okay, and that's 2 cubed times 3 will give you 24. 2 cubed times 3 will give you 24. Yeah, we are able to get 2 cubed because 2 times 2 times 2 equals 2 raised to power 3. Okay, that's why I called it 2 cubed. 2 raised to power 2 is 2 squared. 2 raised to power 3 is 2 cubed. Okay, so the answer for this is 2 raised to power 3 times 3. Now pick another example. Write 315 as a product of prime factors. Write 315 as a product of prime factors. The same thing goes again. Keep dividing by prime numbers until you get to an answer of 1. The previous example we had was an even number, which was 24. But here we have an odd number to start with. That's 315 divided by something else. Now what's that particular number that you'll be using? Check the number. Is it a multiple of 3? If you find that's a multiple of 3, then you start. How do I know if it's a multiple of 3? I look at it very well. 3 plus 1 plus 5 will give me 9. And if 3 plus 1 plus 5 will give me 9, then that means that the number in question is a multiple of 3 and therefore can be divisible by 3. So when you start, you divide by 3 and your answer is 105. Of course, look at it again. 105 can be divided by 3 because 1 plus 0 plus 5 is 6. Okay, and so because 6 is a multiple of 3, then that means 105 is a multiple of 3, and so thereof 105 can be divided by 3. So 105 divided by 3 will be giving you 35. Now at this point you check again. 3 plus 5 is 8. 8 is not a multiple of 3, so it cannot be divided by 3. The next thing you want to check is what's the next thing you can use. Of course, the last digit in 35 is 5. Therefore, this value is divisible by 5. So 35 divided by 5 will give you 7. Now, 7 is a prime number on its own. So 7 divided by 7 will give you 1. Of course. So you pick all the numbers you have used to divide. You check all of them out. You see that they are prime numbers. And of course, they are prime factors of 315. So you write 315 as a prime factor of itself. So you have, to write 315 as a product of prime factors. Okay, so you have 3 times 3 times 5 times 7. And so you are going to write as 3 raised to power 2 times 5 times 7. Okay. Now here's another example. We have 357 as a product of prime factors. 357 as a product of prime factors. Then you go again, you use the same method. The same method works for all kind of questions that fall in this category. Okay, so you have 357 here divided by 3, you'll be having 119. Now 119 divided by 7, you'll be having 17. 17 is a prime number on its own, so 17 divided by 17, you have 1. 17 divided by 17, you have 1. Okay, and so when you write down the answer, you have 3 times 7 times 17. I hope you get that. Now pause the video, write each of these numbers as a product of prime factors. Pause the video and work on all this, and I'll be needing your answer as soon as possible. When you're done, then you play the video. Pause the video right now. Okay, so we have the answers therein. I hope your answer go with what is on the screen. Does your answers go with what's on the screen? If not, check and make the necessary corrections. Okay, check and make the necessary corrections. All right. Can you answer that question? How well did you do? Okay, let's move on. I hope you can see your mistakes now, and I know you'll be able to do well in the next exercise. Give it to you. Now let's talk about real numbers. Let's talk about real numbers. Real numbers can be divided into 2 types. We have rational numbers and we have irrational numbers. Don't forget that in the definition I gave you earlier, I said rational numbers contain integers. Of course, and you know integers contain natural numbers. You can find all natural numbers in integers, okay? And you can find all fractions, all integers, and all natural numbers in rational numbers. Let me repeat myself. You can find all integers, all natural numbers, all fractions. You can find them in rational numbers, okay? So you see, this includes all whole numbers and numbers that can be written as a fraction. Then also all decimals which recur or terminate can be written as fractions. All decimals which recur. When I mean recur, decimals like 0.33333333 and so on, and numbers like decimals like 1.875. Those numbers are terminating decimals. 1.875. There's a stop. There's a termination. There's a stop for them. But recurring, there's a continuous, calling of these numbers, and that's why we have I give you an example of say 0.33333 or 0.666666. Those are recurring decimals. All these kinds of numbers can be written as fractions, and as well, every one of them falls under the class of rational numbers. And of course, you can say that the opposite of rational numbers is irrational numbers. You can see on the screen that irrational numbers are numbers that cannot be written as a fraction. They cannot be written as a fraction. Now, examples of rational numbers are pi and multiples of pi. Pi and multiples of pi, and as well square root of prime numbers. Square root of prime numbers, they cannot be written as a fraction. Okay, pi is not actually 22/7. Pi is not 22/7. Pi is 3.1419 continuously. Pi is not a recurring decimal. Each value in pi is very unique. Okay, and though it may repeat itself subsequently, but it does not form any pattern. Now, square root of prime. What are the square roots of prime? We have square root of 2, square root of 3, square root of 5, square root of 7, square root of 11, and so on and so forth. All these values are prime numbers. So the square root of any prime number is an irrational number. Okay? Now we'll be talking about writing a terminating decimal as a fraction. Writing a terminating decimal as a fraction. Now, write all the digits after the decimal point. Those are the steps you have to check. Draw a line under this. Put a 0 under each digit. Put a 1 in front of the zeros. Now, simplify if possible. Now let's go through the steps. Get a fraction. Get a terminating decimal. Put a line under this. Okay, when they say put a line under this, we are actually saying put a line under all the digits that are after the decimal point, not the ones before. The ones before are the whole numbers. The ones after the decimal point are the ones you should put a line under. Write a 0 under each digit. That's step 3. Now the next one, put a 1 in front of the zeros. Put a 1 in front of the zeros. Now, when you do that, then you can now simplify. If it is possible, simplify if possible means that you express them as a fraction in their lowest terms. Express them as a fraction in their lowest terms. Okay. So let's pick some examples. Look at 0.37. 0.37 can be written as 37. That's the first thing. Put over, then put the zeros. Okay, then you put 1 at the front. You have 37 over 100. Looking at it carefully, 37 over 100 cannot be simplified further because there is no factor that can go in 37 and 100 at the same time. Now let's look at the next one. 0.213. 0.213. The same thing. Write 213 out. Put zeros under each of the digits. Add 1 to the front. And so you have 0.213 to be given to you as 213 over 1000. Okay, let's check the next example. 0.013. Go ahead, write 0.013 out. Write and zeros under, and you have 013 over 1000, which is finally 13 over 1000. Okay. Now, writing a recurring decimal as a fraction. Writing a recurring decimal as a fraction. There are steps you have to follow in this case as well. If the recurring part starts straight after the decimal point, then it's easy. Okay, there are different types of recurring decimals. Something like I told you before, 0.333333. That's it. The recurrence of the numbers started immediately after the decimal point. That's why you have 3333 continuously. Now, if the fraction has 1 recurring digit, it is that digit over 9. If the fraction has just 1 recurring digit, 1 recurring digit means if it is just one number that is repeating itself continuously, one value that is repeating itself continuously, like 0.33333, of course, it's going to be that particular digit over 9. If the fraction has 2 recurring digits, it is those digits over 99, and so on. If the fraction has 3 recurring digits, then it should be those digits over 999. Can you see that? Now I have told you what recurring decimals meant earlier. Let me restate it again. The recurring decimals are decimals that reoccur. The word recurring comes from 2 different words put together. You have re, which is a prefix, and you have occur as a word. So recurring means reoccur. Okay, recurring means reoccur. Now let us talk about recurring decimals in a bit before I move on. 1 over 3 can be written as 0.33333. Okay, and that's a recurring decimal. Okay, that's a recurring decimal. So let's go on and work on some examples. 0.7, you can see a dot on 7. That dot on 7 means that 7 is repeating itself. In other words, if I'm to write this number out in its raw state, it's going to be 0.777777777 and so on. But you can see here that 0.7, according to what we have up here, is going to be 7/9, and that's the answer. 7/9. You don't need to do much maths about it, although there's a calculation around it, but this is the short form. This is what you're expected to know. So 7/9. Okay, now 0.38, here we have two recurring digits. If I'm to call this one, this is 0.383838383838 and so on and so forth. So two recurring digits means that the digits will be over 99. That's 38/99. Of course, there's no factor that can go in 38 and 99, so that's the final answer. And let's go to the third one. We have 0.462, 0.462 with a dot on 4 and a dot on 2. This means that this number starts recurring from 4 and the recurrence stops at 2. So if I'm to call this in its raw state, it's going to be 0.462, 462, 462, 462 and so on. Okay, so it is starting with 4 and ending with 2. Now you may ask, why is there no dot on 6? Yes, there's no dot on 6 because it's not necessary. Already the first dot shows where the recurrence starts from, the last dot shows where the recurrence ends. So what the values that are in between the dots shows the amount of figures you have to write first. So you are starting with a 4 and ending with a 2. So if I'm to write this, let me repeat myself. If I'm to write it in this raw state, I'm going to write it as 0.462, 462, 462, like that continuously. Okay. Now look at the statement written about 3 recurring digits, which is up there. You'll be having 462/999. Now, if you have a doubt in your mind about the answers, go to your calculator, punch the fractions you have right on the screen, punch them into your calculator and see if you get the raw state of the recurring decimals or exactly what you are seeing on your screen right now. Put the fractions therein and see what you get. Okay. Alright, have you been able to do that? Okay, now let's proceed to the next stage. If the recurring part doesn't start straight after the decimal point, then we can express the decimal as a fraction by using method as illustrated in the following examples. By using methods that are illustrated in the following examples. Okay. Look at this example here. 0.73 with a 3 with a dot on 3. You can see that the dot is not starting from 7, it's starting on 3. So what would you do? The first thing is represent a letter to be 0.73. The next thing is scale up the above recurring part so that the recurring part starts straight after the decimal point. Okay, scale up the above. How do you mean to scale up? Move the decimal point. Okay, now if you want to move the decimal point, how would you do it? If I multiply 0.73 by 10, I will say that the decimal point will shift to the back of 7 instead of staying at the front. If I multiply by 10, it will shift to the front so that I can have 7.3. Then you can see that the recurring part will start after the decimal point. Okay, and so I can scale up the above to line up recurring parts. I scale up the above to write the recurring part, and so I have 100x to be 73.3. What does that mean? 7.3 can be written as 7.33333, as explained to you in the last video. So if I multiply further again by another 10, I can scale it up and bring the decimal point to the back again of 3, so that I can have other 3's. Okay? And by so doing, all I just need to do was subtract the two equations that I have there, 10x, 100x. Okay? So when I do that, I have 90x to give me 66. Of course, 73.3 on the dot plus minus 73.3 will give me 66. Let me say that again. 73.3 minus 7.3 will give me 66. Okay? Of course, the values, the recurring values that after decimal point will cancel out and give me 0. Then I also have 100x minus 10x will give me 90x. And of course, x is going to be 66 over 90. X will be 66 over 90, which can be further simplified to be 11 over 15, which can further simplify to be what? 11 over 15. Now let's do another example. 0.58 here. 0.58 can be written as x to be equal to 0.58. The same thing we did in the previous one. We scale up. When we scale up, that means we move the decimal point. When we move the decimal point from the left to the right, that's 10x. You're multiplying by 10, so that I can have 55.8. Move it once again, so that will be 100x to be 58.8. Now you can see you have a similar value on this side. 8 with dots on their heads. Okay, so you go ahead and subtract, and when you subtract, you have 90x to be equal to 53. Why? Because the decimal part will go away. Okay, so when you finally resolve the equation, you are going to be having x to be equal to 53 over 90, which of course is your answer. Now we go to another example right now. We have 0.658. 0.658. Here it's a different question, but also the same method. X to what? To be x to be equal to 0.658. For every recurring decimal that doesn't start from the number after the decimal, this is how you are expected to solve it. You represent x to be that particular recurring decimal. Okay, and when you do that, you scale up. Now when you see that you scale up for 10, what do you have? 6.58. Now in this case, after scaling up for 6.58, if you scale up for the next one, which is going to be 100x, you'll be having 65.58. Okay, which is not right, but you want to do it rightly. You will scale up 2 times so that you can move to the next value, okay, which will be 658.58. How do you get to 658.58? If you scale up once, you'll be having 65.8. Oh, that's the right thing. Sorry about what I said the other time. 65.8. Now, if you scale up one more time, you'll be having 1000x, which is going to give you the right value. You want to scale up in such a way that the recurring value will still be there at the end. We'll still have the same thing in common with what we have done before. Okay, that's why you have to scale up 2 times. Okay, because of the recurring is starting from 5 and ending with 8, so it will be 585858. You want to stop at an exact spot where you have a common value with the first one, and after doing that, you subtract both equations. You'll be having 990x to give you 652, and x is going to be 652 over 990, and finally you're going to be having 326 over 495. Of course, you should know how to do this already. This is not really something that is big. I mean the part where you divide into the lowest forms. You just look for factors that are growing in 652 and 990, and you solve the problem. Now, here's another question. 0.174. 0.174. Of course, what we're doing here is representing x to be 0.174. As usual, we follow the same method. We have 10x to be equal to 1.74 with the dots on 7 and 4. Now you scale up again. Look at how much times you have to move to get to the next value. You'll be having to move twice, okay? And when you move twice, that's 1000x, okay? 1000x to be 174.74. And by the time you do your subtraction, you'll be having 990x to be equal to 173, and x is equal to 173 over 990. And that's your final answer. Let's take one more example. We'll be having 0.369. 0.369. Here, x will be equal to 0.369, and so we do 10 to be equal to 3.69. Now, to scale up again, you see for every value that has the recurring decimal starting from 1 and ending at another, whereby you have two of them that will be recurring, and they are together, compactly together, you know what you have to do? Just scale up 2 times, okay? Like in the previous example. So you'll be having 1000x to be 369.69, okay? And by the time you subtract, you'll be having 990x to what? 366. And x equals to what? 366 over 990. And that's 61 over 165. Okay, so that brings us to